Okay, picking up where we left off last class, we had talked about valence shell electron pair repulsion theory, the idea that our electron groups, our lone pairs, and our bonds, single, double, triple bonds, are all made of electrons. Electrons are negatively charged, and so they're going to spread out as much as possible. And so that's when I was doing these fun poses and getting rid of things and all that sort of fun stuff. We are going to build on that idea, and that idea itself built off of Lewis structures, which we'll be doing a worksheet on in class or in lab today. So we're building off of what we built off of, and so building off of that valence shell electron pair repulsion theory, we're getting into topics of electronegativity and polarity. So you may know that if you combine oil and water, like in this picture, right, they'll separate out. Go ahead and stir it up, and then if you leave it for a while, it still separates out. You shake it up, it separates out. It's not really mixing. You can sort of get them to associate with each other, but at the end of the day, they're always going to separate out. And the reason is that the water molecules like each other more than they like the oil molecules. The oil molecules like each other more than they like the water molecules. So they end up separating out. But why do they do that? That's what we're going to be getting into. If we look at a water molecule, like the H2O that's pictured here, we could represent this with its actual geometry, the bent shape. In a water molecule, our oxygen and hydrogen atoms have both donated one of their electrons, one of their valence electrons in to form that bond. So they've each put in equally, but they are not sharing equally. In reality, the oxygen atom is holding those electrons closer to itself. So it's pulling or holding those electrons from the bond. It's actually holding those electrons closer to itself. The hydrogens have a little bit less of the share of the electrons in that bond than they should if it was equally distributed. And the oxygen has a little bit more. Oxygen, we say, is more electronegative than hydrogen, and so those shared electrons are more likely to be found near the oxygen rather than by the hydrogens. So if we drew that bond with a little bit of shape to it to represent where the electrons are most likely to be found, they're more likely to be found close to the oxygen. So we can draw it a little bit wider there. They're more likely to be close to the oxygen than they are to the hydrogen because of the property of oxygen being more electronegative. Electronegativity is the ability of an element to attract electrons, to pull electrons in a covalent bond. I think of electronegativity within a bond as like a tug of war. So oxygen has a stronger pull than hydrogen. And so in that tug of war, since oxygen is pulling more strongly, the electrons are closer to the oxygen. And we've got rankings for pretty much all of our elements, all the ones we care about at least. It's a relative scale. It's not an absolute scale. So 4 is the strongest electronegativity value. And that belongs to fluorine. Fluorine holds the 4. Nobody else has a 4. Everything else is less than 4. So if any other element gets into a bond with fluorine, fluorine's the big guns of pulling electrons, and so fluorine is going to win that tug of war battle. Those electrons will always be closer to fluorine than they are to the other atom or the other element. Because of that unequal sharing of the electrons, the oxygen atom has a partial negative charge, symbolized by, I think that's sigma. So that's our symbol for partial negative charge. It's not a complete negative charge because it hasn't stolen the electron. It's just that it's closer to it most of the time, and so on average, it's a little bit more negative around the oxygen. The hydrogen atom, on the other hand, since it's lost some of the electron density, has a partial positive charge. And that uneven sharing, draw the oxygen and the hydrogen there, that uneven sharing of the electrons results in what we call a dipole moment. The di as in 2, poles as in plus and minus, like poles of a magnet or poles of the Earth. And a moment because it's sort of temporary. Not 100% sure why the moment's there, but we call it a dipole moment. So that uneven sharing causes hydrogen and oxygen to have partial charges. Again, not full charges, they're relatively small charges compared to ions that are like sodium plus or fluorine minus, fluoride. If we have covalent bonds, like between hydrogen and oxygen, between basically any of our nonmetals, if those have a dipole moment, we call them polar, having poles, or a dipole moment. And if we have a greater electronegativity difference, the charge separation, or just the charge, is bigger. So like fluorine is our value of 4. If that's bonded to oxygen, I think oxygen is 3.5. So this difference is 0.5. That will have some amount of charge separation, some amount of dipole moment. We could call that a polar bond. If we have fluorine bonded with nitrogen, or maybe carbon, because carbon's even more weak, I think carbon's a 2.5 compared to fluorine's 4. Then our difference of electronegativity is 1.5, right? And so we're going to have a larger charge difference, larger partial positive, partial negative. In that bond, because the difference is bigger. For electronegativity, our general trend is that fluorine reigns supreme with a value of 4. And we increase electronegativity as we move left to right and as we move down to up. This, from the book, is showing decreasing electronegativity as we go down. So basically, up and to the right, we're increasing in electronegativity for the most part. If you look at your yellow sheet, you actually have electronegativity values on there. So if you look at fluorine and find the 4.0, I think it's in the bottom right-hand corner. That 4.0, that's the electronegativity value. That's the only one probably you should have memorized. Not to say that you can't memorize the other ones, but that's the most important one. If we have an electronegativity difference that is really small or basically the same or exactly the same, like between two of the same element, then the electrons are shared completely equally and there's not a dipole moment. So this will happen every time that we've got a bond between two atoms of the same element because they have the same strength for pulling the electrons. And so it's a dead tie because their electronegativity, their ability to pull those electrons closer to themselves is exactly the same, and so nobody's winning. They're actually sharing those electrons evenly. And that's one case of a nonpolar covalent bond. There's no partial charges formed. Because the electrons are shared evenly. So F2, all of our other diatomic elements, all of our Brinkelhoff, our Horse's needle oats for clear brown eyes, those are always going to have nonpolar bonds. If we get, on the other end of the spectrum, a very large electronegativity difference, more than in a polar bond, then that pull, that electronegativity difference gets so big that the one with the higher electronegativity just steals the electron. And that's what's happening in ionic bonds. Remember that ionic bonds are between metals and nonmetals, because that's an ionic compound. So anytime we've got a metal and a nonmetal, we should expect to have an ionic bond. And the nonmetal is going to be the one that steals the electron. Our nonmetals are in that upper right corner of the periodic table, closer to fluorine. They're going to have higher electronegativity values. Our metals are going to be kind of more towards the left side of the periodic table. They're going to have a lower electronegativity value, weaker electron pull, and so they're going to tend to give up their electrons. That's another property that we know of metals, is that they tend to lose electrons. So in this case, our nonmetal is stealing the electron from our metal. And the intermediate one that we looked at previously, in between polar and, or in between nonpolar and ionic, is polar. typically going to be between two nonmetals. I think for us, it's always going to be between two nonmetals. Here's a general rule of thumb, general guidelines for whether something's covalent or nonpolar, polar, covalent, or ionic. So our cutoffs are basically 0.4 and 2. So if it's below 0.4 in terms of electronegativity difference, then that's going to be pure covalent, aka nonpolar. If it's somewhere in the middle between 0.5 and 2, then that's what we would call a polar bond or polar covalent. And if it's greater than 2, then it's ionic. And we've got a couple of special cases that are always going to be nonpolar and a couple special cases that we expect to be ionic. So for nonpolar, anything that's, for example, F2, N2, O2, etc., if it's something bonded to itself, the electronegativity, they're going to have the same value. And so our difference between those two is going to be 0, so that's always going to be nonpolar. We don't have to know what the electronegativity value is. And if we've got an ionic compound, something that's a metal and a nonmetal, then we can expect that to be an ionic bond. Regardless of what the actual electronegativity values are. And this kind of works on a spectrum, so it's not like real hard, fast lines. These are kind of just general rule of thumb, ballpark numbers. All right, for each of these compounds, you can use your yellow sheet because you've got the electronegativity values on there if you need them. Is the bond formed between each pair of atoms pure covalent, aka nonpolar? Is it polar covalent, polar? Or is it ionic? So go ahead and try to identify those. So if we look at our yellow sheet or a table, periodic table with our electronegativity values on them, we can find all of these on there. For nitrogen, we'll find electronegativity value of 3. So if we've got a bond between nitrogen and nitrogen, 3.0 minus 3.0 means that our electronegativity difference is 0. So that's going to be nonpolar or pure covalent. You could also just identify it's the same thing. It's going to have the same electronegativity value. It's going to be nonpolar. Or it's the same thing, so it's nonpolar. Either of those ideas works for me. For Rb and Cl, Rb rubidium has a value of 0.8. Chlorine, Cl, has a value of 3.0. So we do 3.0 minus 0.8, and we get a difference in electronegativity of 2.2. That's above our threshold of 2 for an ionic bond, and so we would call this ionic. Another way that we could identify it as such is that rubidium, Rb, is a metal, chlorine is a nonmetal. That makes it an ionic compound, and ionic compounds have ionic bonds. So that would be another way to identify it. And then for C, we have phosphorus, which has a value of 2.1. and oxygen, which has a value of 3.5. So to calculate our difference in electronegativity, take the 3.5, subtract 2.1. That gives us a difference in electronegativity value of 1.4. That's between our 0.4 and our 2. So we call that a polar bond or a polar covalent bond. There's also a mnemonic device for remembering. It's not 100% accurate, but it's okay for remembering electronegativity values. And it's Fonkel brick ship. For some reason, this one has stuck with me for like 10 years, Fonkel brick ship. So if you're ever in a pinch and you just, somebody's threatening you, maybe with a bad grade, if you don't get your electronegativity order correct for the most electronegative elements, there you go. Fluorine's the goat with a 4, and then it's all downhill from there. The only thing that I don't like about Fonkel brick ship is that you have to get the iodine in the right spot. Because it feels like it can also go between the hydrogen and the phosphorus, but it actually goes earlier. So realistically, is that going to help you? Probably not, but I think it's fun. It is a little bit silly at least. Okay, so that's just looking at individual bonds. We're going to build off of individual bonds though. So we can move out of just bonds into thinking about entire molecules. So molecules can also be polar. And a polar molecule has an overall dipole moment. An overall, over the whole molecule, charge separation. That's all the dipole moment is. So across the entire molecule, however you want to look at it, whatever orientation, you'll find one part that's partially negative and other parts or part that is partially positive, and those will be separate from each other. So applying that idea of pulling electrons within a bond, if we apply that over a whole molecule, electrons are more likely to be found on one side of the whole molecule as opposed to the other, and that creates partial negative, partial positive charges. And this is where our valence shell electron pair repulsion theory, the shape stuff that we were doing last class, comes into play. A couple of simple situations though. If we have a diatomic molecule, like HF has a polar bond. 4.0 minus 2.1 gives us an electronegativity difference of 1.9, so this is a polar bond. And since that's a polar bond, and this is the whole molecule, right? Fluorine's going to be hogging some of the electrons. Hydrogen kind of winning the battle. It's going to be partially positive. There's nothing to cancel out that electron pull. So fluorine's winning the battle. Fluorine's going to hold a partial negative charge. Our hydrogen is going to hold a partial positive charge. So diatomic molecules, if it's a polar bond, it's always going to be a polar molecule. So that is a polar molecule. And I feel like every time I try to do these sigmas, it looks like a little music note. So my apologies. If we have more than just 2 atoms, then we've got potential for that pull to get canceled out. So with multiple bonds, polar bonds can cancel. So this is sort of the most basic scenario. If we think about people, let's say that we've got a little tiny person and they're playing tug of war with two people at the same time for some reason. And the two people that they're playing tug of war with are huge, just absolutely jacked. Right, large individuals, absolute specimens of physicality. This person in the middle is in for a bad time, right? They're going to be getting pulled really hard one way, really hard the other way. However, if you notice, the people on the outside are the same size, so this person in the middle is kind of just along for the ride, and those people are playing tug of war through that small person. So who's going to win between the two big people? Nobody, right? They're the same size, they're pulling with the same strength, and so those pulls cancel each other out. So they're just at a dead standstill, ripping this small person apart in the middle. Hopefully their grip gives out. So these pulls cancel each other out. So there's no net movement in this tug of war battle, even though we have those big differences in pull strength or in electronegativity. So we're going to look at some cases of that happening within molecules. Carbon dioxide is the one that we'll be looking at, and it's that exact situation. So carbon dioxide has polar bonds between our carbon here in the middle and our oxygens on the side. So within this bond, the carbon and the oxygen, there's a pull represented by this arrow, this pull. So it points in the direction of the negative, and then the other side makes a little positive sign. Let me make that a different color. Yeah, red's a good contrast. Right, so you can sort of see there's a positive side. So we're pointing towards the negative. The oxygens are pulling the electrons, so they would be getting the partial negative charge. And then carbon would be getting the partial positive, but because they're pulling in completely opposite directions, those cancel out. So the differences in electronegativity cancel out. Since they are opposite in terms of their direction, and it's the same strength. So this is that case of big people on the outside, little person in the inside. That's what we're looking at here, but with pulling electrons instead of pulling a rope, a tug of war. So even though it has polar bonds, it's nonpolar. The way that I think most people don't like to think about it is representing polar bonds with vectors. So we showed it there as arrows. Arrows are basically just vectors, so it has a direction and it also has a magnitude. They point in the direction of the negative. And this is good to know. This arrow notation is good to know. So they point in the direction of the negative, and then they've got a plus sign on the positive side. If they're pointing in a way that they all cancel out, which for things in a line, pretty easy, pretty nice, that works. If they're pointing in opposite directions, equal size, then they'll cancel out. It starts to get weird when we get into 3 dimensions, which is why I feel like people don't like to think about the vectors part of things. And we'll see that in a little bit, possibly sooner than we want to. Water also has 2 bonds, and it has 2 polar bonds, but because of its shape, it has the bent shape, the dipole moments don't cancel each other out. So if we just draw in the atoms, we've got our oxygen in the middle and our hydrogens on the sides. These arrows are not pointing in completely opposite directions. We can see that they're both pointing slightly up as well as inward. Those inward forces are going to cancel, but that slightly up bit that they have to them, this is the part that makes thinking about them as vectors, I think, upsetting to people, maybe. So these arrows pointing in cancel each other out. They said something they weren't supposed to, they're canceled. These arrows that are pointing up, however, do not cancel out, so those are actually adding to each other. So we have a net dipole moment of a partial negative up top and a partial positive down below. And let me change these colors. So because of its shape, and it has polar bonds, the polar bonds don't cancel out, they add up, and so it's a polar molecule. So polar bonds, and they don't cancel. So H2O is polar, or is a polar molecule. And this is where the valence shell electron pair repulsion theory comes into play, because we could draw out a Lewis structure for H2O, and if we didn't know that it was built this way, if we didn't know that it had this bent shape, we might think that those arrows would cancel each other out. And so we would think that it's nonpolar, but because we know that those electron pairs repel each other, we get that bent shape, and so they don't cancel out, making it overall a polar molecule. If you don't like thinking about any of this and you just want to memorize stuff, there's a simple breakdown. Since we only have 5 shapes for this class, and we're generally going to be dealing with stuff that has the same bonds across everything, you can memorize these cases. So we've got 4 shapes where if we have polar bonds, 3 shapes, and I'm also looking at one of those because there's some problems here. It's fine. It's no big deal. The 2 shapes that are down here for nonpolar, we've got our trigonal planar, we've got our tetrahedral. We should also have down here linear, like our CO2. So some of these shapes, if it's linear and it's more than 2 things, it's the same bond on both sides. Those arrows are going to cancel out. If it's trigonal planar, all of these arrows cancel each other out. If it's tetrahedral, all 4 of these arrows cancel each other out. For our polar things, we've got a couple of our shapes up there. We've got diatomic linear, If we have a polar bond, then it's polar. We've got trigonal pyramidal. Those arrows also add up. And then the last one's tetrahedral, but we've got a different bond between the carbon and the chlorine. And I think the one that I would add to this is like our H2O. So a bent shape. If that's confusing you, don't get concerned yet. All right, if we want to determine whether a molecule is polar, we first need to determine whether it has a polar bond. A polar bond must be present for it to be polar, for it to even have a chance of being polar. For it to be able to be polar. If we don't have a polar bond, it can't be polar. That would be the faster thing to write. So that's our first check. Do we have a polar bond? If we don't have a polar bond, congratulations, it's not polar. If the answer is yes, then we have to figure out if the bonds add up. Do the bonds cancel each other out? If they do cancel each other out, then it's nonpolar. If they don't cancel each other out, then it's polar. And the question about whether they cancel each other out requires us to use valence shell electron pair repulsion theory. There is a fun, I think it's fun, method for figuring out whether they're polar or nonpolar. And this is affectionately referred to as Mrs. K's alternate method for determining molecular polarity. Mrs. K not being my wife, also not being me, rather my mom. So Mrs. K's alternate method for determining molecular polarity. This is the quick way of figuring out if something is nonpolar. So first step, we need a Lewis structure. So we have to be able to put together good Lewis structures. And we look at our central atom. If we have no lone pairs on our central atom, and the bonds are all the same, or they have the same difference in electronegativity, then the molecule is nonpolar. And as nice as it is to memorize Mrs. K's alternate method for determining molecular polarity, I think that this fast method for determining molecular nonpolarity is better summed up, or better called the nonpolar express. So this is the nonpolar express. If we have no lone pairs and the bonds are all the same, it is nonpolar. This also works nicely if either is false, then it's polar. this assumes that we have a polar bond. So this is a nice separating factor. Lone pairs, all the same bond, just two things to check. If both of those are true, but there's no lone pairs, then it's nonpolar. So let's look at an example. We want to determine whether CH4 is polar. The first thing that we want to check before we start a problem like this, because we're looking at if the molecule is polar, in order for it to be polar, it has to have a polar bond. So does it have a polar bond? We have carbon bonded to hydrogen, so we're going to have CH bonds. Carbon has a value of 2.5. Hydrogen has a value of 2.1. So the difference there is 0.4. That is right on the threshold of polar, nonpolar. So we could argue it's not polar. And then that's it, it's not polar. That would be one way of coming up with the answer. That's the fast way. We could also, just to do our due diligence, come up with a Lewis structure. The Lewis structure that we would probably come up with would look like this. Carbon in the middle, 4 bonds to hydrogens. We have a total of 8 valence electrons. That fills up with 4 bonds. So it's a quick one to put together. And then we can do our valence shell electron pair repulsion theory. Or we can use the nonpolar express. So let's do the nonpolar express. Our two conditions are that we have no lone pairs on the central atom, carbon in this case. Do we have any lone pairs on carbon? No, we do not. And so this meets our first condition. And our other condition for the nonpolar express is that all bonds with the central atom are the same. Is that also true? Are all bonds the same? They are all the same. And so CH4 is nonpolar. It meets both conditions for our nonpolar express, and so it is nonpolar. Alternatively, you could memorize that the tetrahedral molecular geometry is going to be nonpolar, but that's kind of baked into the nonpolar express. So I think this is a better method, just memorizing these two conditions rather than memorizing all the individual shapes. All right, let's do the same thing for NH3. The first thing we want to check, do we have a polar bond? This time we're going to have nitrogen bonded to hydrogens. Nitrogen's electronegativity value is 3.0. Hydrogen is still 2.1. So our difference in electronegativity is 0.9. That is between our 0.4 and our 2. So that's in the polar zone. So we have a polar bond. It's between our 0.4 and our 2, so we have a polar bond. So we do have to continue on. We can't just say, no, it's not it doesn't have polar bonds, it's not polar, like we did with CH4. We do have to actually draw out the Lewis structure. So I'm going to assume that we can come up with a Lewis structure for NH4, and you would probably come up with something that looks like this. Nitrogen bonded to 3 hydrogens plus a lone pair on nitrogen. So maybe take a moment, think about whether this is going to be polar or not. So let's check our nonpolar express. So our two conditions, the first one is no lone pairs on our central atom, in this case nitrogen. Do we have no lone pairs on nitrogen? We do have lone pairs, so we don't not have lone pairs on nitrogen. We do have lone pairs. So it fails the first condition. So this is not nonpolar, or the less confusing way of saying it, it is polar. It fails the nonpolar express, therefore it's polar. If we wanted to draw this out in the 3D shape, we have 4 electron groups. We're going to have tetrahedral electron geometry. We can put one of our groups, our lone pair, up top. We can put one of our hydrogens in the plane of the board. Another one is going to be coming out towards us and on the right. And the other one is going to be kind of going back and to the right. And so our 3 arrows sort of confusing looking. But in like 3D space, we would have one shooting up here, another shooting up here, and another shooting up here. And so they're all going to add up in the vertical element towards that lone pair. If we hit our tetrahedral shape and get rid of one of the groups, right, if my legs and one of my arms are all arrows pointing towards me, they're going to add up in that 4th direction. I kind of look like I'm channeling lightning in Avatar. So that would be the other way of thinking about it in the vector arrow sort of way. We have questions so far on electronegativity, polarity, nonpolar, ionic, nonpolar express. Okay. Then I give you this one. Determine whether SO2 is polar. And I'll give you a couple minutes to work on that. All right, the first thing that we want to check, I'm just starting it, right? The first thing we want to look at is, do we actually have a polar bond? So do we have a polar bond? We've got one sulfur that's probably going to bond to the oxygen. So we'll have some sort of sulfur bonded to oxygen bond. Sulfur has a value of 2.5. Oxygen has a value of 3.5, and so our difference there is 1.0. That's very solidly in the polar region. So we do have a polar bond. So we do have to continue and come up with a Lewis structure and then check it with our nonpolar expressor, thinking about it in terms of arrows and vectors and angles and all that fun stuff. So our shape for, or our Lewis structure for SO2, we've got sulfur in the middle so that it's symmetrical. our oxygens on the side, we're going to have 18 valence electrons. Each of those has 6 valence electrons. They're in the same 6A group. To get things connected, we put in a set of bonds, 2 bonds, for our minimum bonding electrons of 4. So we have 14 remaining electrons. We'll place those then starting from the outside and working our way in. So we can place 6 electrons on each of the oxygens. We can't place any more than that because that gets them up to their full octet, because 3 lone pairs plus a bond is 8 electrons. So the most that we can add to our oxygens is 6 each, which is 12. And then we have 2 left, and so those will go onto the sulfur. So that's all of our electrons up and on the board. If we check our octets, oxygen is happy. Both of them have their full octet because of those 3 lone pairs plus the 1 bond. Our sulfur, however, not happy. It has 1 lone pair and 2 bonds. That's only 6 electrons. It needs 2 more. So we have to pull in either from the left or from the right in Orange Go Tigers to make a double bond, one of them. So we got within its 2 wolves, within our Lewis structure, 2 structures. But let's not worry too much about that. It doesn't really matter here. So we'll have that Lewis structure or it flipped left, right for our other Lewis structure. Okay, so work from there. If you hadn't gotten there, or if you had already gotten there, or whatever, work from there, see if you can figure out whether it's polar or not. So the check down list that we go through, we're looking at our nonpolar express. Our first condition, no lone pairs on the central atom, in this case, sulfur. Is that true? Do we have no lone pairs? No, we have lone pairs. We have a lone pair on sulfur. SO2 is polar. This also has the bent molecular geometry that like H2O has. So the arrows that we can draw for this if we separate these arrows into left, right, and up, down, the left, right part is going to cancel out. The up, down part does not cancel out. That adds up. So the vector way of thinking about it, these arrows add up, will have an overall separation of charge, overall dipole moment, so it's polar. Questions about that exercise? All right. So getting back to oil and water and why they don't mix. Water molecules, as we saw earlier, are polar, and oil molecules are nonpolar. And there's a saying that I don't think that we've come across, but maybe we have. The saying is that like dissolves like. So polar dissolves polar, nonpolar dissolves nonpolar. This applies for liquids as well. If you mix a polar liquid with another polar liquid, they'll mix together. So like if you mix ammonia and water, congratulations, you've got like Windex basically. Those will dissolve into each other. They'll mix and mingle with each other nicely. if you get something that's polar with something that's nonpolar, typically those don't like each other very much and they will separate out. The way that they're attracted to their respective molecules is different. Polar molecules have this dipole moment, and so they'll stack up like little magnets in the water. And this happens when water freezes, especially. So they'll freeze into these alignments with the partial positive charge on the hydrogen matching up with the partial negative on an oxygen. Nonpolar molecules interact in a way that I think of more as friction. So they're typically really long, and they can sort of get tangled up on each other, or you can think of it like long pieces of spaghetti kind of sticking to each other. Individually, they're not especially sticky. Like if you just get a little bit of spaghetti on your finger, right? You can pull it off pretty easily. But when you've got a whole mess of spaghetti all together, that stickiness kind of adds up and globs up. So you might add a little bit of oil to get your spaghetti to unstick from itself. It's also kind of like putting pages of a phone book together. When you're lacing them all together, you could pretty easily undo all the pages and pull the phone books apart. But if you try to pull it apart, it's not going anywhere. Like the Mythbusters episode where they pull a truck or whatever with the phone books together. That's sort of how nonpolar molecules interact. And because they interact in different ways, the polar and nonpolar molecules don't interact nicely with each other. However, there's a workaround, and that's soap. So soap is our workaround for getting polar molecules, water, to interact with nonpolar molecules like oil. Soap has a nonpolar tail. So we've got an example of what soap might look like down below. So this interacts with oil. And then we've got a polar part that can act with water. So this is why using soap helps clean oil off so well. We've got this polar part that can latch onto water molecules on the right. We've got the nonpolar part over here that has this sort of same spaghetti-looking structure to it. And so this long surface area will interact with the weak surface area forces of like oil, for example, and that gets the water to latch on indirectly to the oil, so you can pull the oil off your skin with water. And now you know how soap works. Isn't that fun? Questions? Yes, question.
I don't want to sound like silly right now, but like you know how like in the ocean,
Yeah.
it's like separated, or like when one part. Does that have anything to do with that?
What being separated in the ocean?
Like salt water, fresh water.
Oh, I mean the ocean's all salt water. That's just because of mixing. But like when you have fresh water that rushes in, you get like brackish water kind of at the intersection. It's not related to this. That's just where there's dissolved ions or not, basically. But there is also fun chemistry with that. We just won't talk about it. Other questions? Okay.